Okay, so welcome to chapter 2 now. This is chapter 2, common mistakes and how to avoid them. So there are 4 parts. Common mistakes, checklist for avoiding common mistake, a systematic approach, and a case study. So, common mistakes. So I have a list in the book of 50 different, I think, I don't know, I don't remember the number, but a large list. Here we'll just go through some top ones. Most common one actually is no goals. So, and the reason is basically you start a thesis project, or in a company you start a development project, and then they hire a performance analyst to do the performance analysis, but he or she has no idea what is supposed to be done. So it's supposed to be done. And if you have no goals, you cannot do any really useful work at all. And so there is no such thing as general purpose performance analysis. And there is no general purpose model. So first thing you need to set up is the goal, that we want to improve the performance, we want to we want to characterize the performance, we want to do whatever you want to do. You have to clearly state the goal, and that will determine whether what technique you use, what metrics you use, what workload you use. For different goals, the techniques are different. Like we gave example last time for, something is good for software, something is good for hardware. So we need to know what exactly you want to do. And setting the goal is not trivial either, because in the real world, the goals keep changing. The world is not static, so you might be thinking of going south, but on the way you decide, no, you want to go north. Every time you take a turn, you have to change. So this thing, just kind of a cycle, is that goals determine techniques, metrics, and workload, but the goals change. But without the goals, you are not going anywhere. Biased goals. Second thing is sometimes the goals are biased, so they are not really, that could be the case, that to show that our system is better than theirs. And maybe that is the case. The analyst's job should be that of a jury, that this should be not biased. So here is the thing, generally, I don't know that is true in the real world, but in the real world, you are pressured to produce results that satisfy what they are paying you for, right? Which means show that ours is better than theirs. But what you have to do is, still you have to come up with, you have to know how to do it correctly and unbiasedly. And then whatever bias methods, if you're expert, maybe you can just tell them that if you did it this way, maybe it will come out better, but this is the right way. All right? So that is the thing, is not to be biased towards that. Unsystematic approach. And then once you know the goals, then people just go haphazardly. And so there is a systematic method that we'll talk about. Analysis without understanding the problem. And so, as they say, understanding the problem is half the work. If you don't know the system, you don't know the problem, then you cannot do the analysis modeling. So you really have to understand. So if you have been asked to analyze a database system and you are a very queuing theorist, you can't start until you understand the database systems, right? Incorrect performance metrics. So then start the list of things. So basically, once you have the goals and once you understand the problem, it is quite possible that you didn't use the right metric. And unrepresentative workload. You didn't use the right workload, or you didn't use the right technique. Those are the top 3.
Can I ask you a question?
Yeah.
Can you give us I want to understand where is the bottleneck? How do you
Okay, so we have actually a case study coming up, examples coming up, but say I want to understand the performance is not a goal, because you have to say I want to understand how many MIPS this system has, something like that. Otherwise, you don't even know whether it is hardware or software you need. Right? So it has to be more specific than just knowing the performance. So you have to say, let's say you are working on some algorithm. You have to say, well, I have to measure how many seconds does it take. something which gives you the direction where to go. Yeah.
Do I need to know the exact workload at the beginning of my work?
No, we will tell you how to find the workload. No, but the thing is, I'm telling you all this actually when people have spent quite a bit of time, or they have probably published a paper and then we find out that they used the wrong workload or they used the wrong metric. It is at the end of the study.
But I can change the workload during my work, right?
Of course. The thing is, you will be correcting your mistakes. You are driving towards some place and you find that you are in the wrong place. So you will be changing directions. But when you are done, if you are at the wrong place, then it will be big trouble, because, see what I mean? So this is at the end of when the paper has been published and we are reviewing the paper and we find that the approach is not systematic, that they don't understand the problem, that they had the wrong metric. Okay? Overlook important parameters. So they just concentrated on something, changing something, we change x to y to this, but they forgot that something else is really the key, which is also changing along with it, and that is affecting the performance. Ignore significant factors. So there are two things, parameters and factors. Parameters are things that affect the performance, such as room temperature could be a parameter. But factors is a thing that you are really trying to control or study. So you are really not, you are just trying to control how many users there are and what is the performance of my system for 10 users, 20 users, 30 users. But if the room is very cold, the performance will be very cold. I mean, in the sense that the people are not going to do too much work there. I mean, and so performance will be affected. The numbers that will be measured will be affected. But you just say, well, I am not going to worry about room temperature. I'm not going to worry about wind velocity. I mean, things like that. Those are indirect things, right? So those are parameters, but not factors. So this is a technical term. Factors are like when we do the analysis, we say full factorial design. Factors are things that we are changing, controlling, and measuring and monitoring. Parameters are the things that some of the parameters we don't want to control. We just keep them as a noise, right? So ignore significant factors. Inappropriate experimental design. So as I said, a lot of people don't know about the experimental design, and so they will just do it wrong. Inappropriate level of detail. And everybody thinks that the more detail they go into, the better model it is. And the answer is wrong. So I was working with this guy who was doing this simulation he was writing simulation for almost 2 years, and I kind of got tired and asked him, why are you doing for this? He said, no, I am going through very much detail. I am simulating everything in this system that goes on in the system. I said, like what? He says, I am simulating how the arm moves inside the disk. And I simulated arm movement inside the disk, So I said, how do you know how the arm moves inside the disk? He says, well, exponentially. I said, if you know it is exponentially, then why do you have to simulate it? I mean, the thing is that you can go into detail, but you really don't know how the arm moves. So you are going to put some assumption which is totally invalid, right? And if it is invalid assumption, garbage in, garbage out, your result, how long did it take for the disk to do whatever it to do was wrong, because you just assumed exponential, right? So if you don't have a data about something and you are simulating it, I mean, what is the point? You have to simulate things that you know about, so then you can get the answers that are somewhat correct. Otherwise, if you just detailed simulation, the input is wrong, the output is going to be wrong. So that's the kind of thing, So there is no need to simulate something that you don't know about. All right, no analysis. And then there are three kinds of people. Some people who are very good in queuing theory and mathematics, and for them every problem is a queuing theory problem. Then there are some people who are very good programmers. They don't know queuing theory, of course, and so for them everything is a real hands-on measurement problem, and they will not do any analysis. So you give them a problem, they will come back with a result so big and say, here is my measurement, to impress, such a thick, 400 pages, and what is boss going to do with that 400 pages? They can't read it, they can't present it to the customer, they can't use it. and as soon as the person walks off, they just file it away in the round bin. And so the idea is that's no good. You really need to analyze. Right? Your job is not just measuring, your job is to analyze. No analysis. Erroneous analysis and then incorrect analysis. No sensitivity analysis. So you make a conclusion, you say, well, the right value for this parameter is 5. But if you did not do the sensitivity analysis, what if it is 5.5 or what if it is 6? How much does it vary? So the thing is, it is quite possible that 5 and 6 are same, or 5 and 10 are same. It is very flat surface, as opposed to being a very peaky surface. So it doesn't matter where you are in that parameter range. Right? So you have to do that sensitivity analysis. And if you didn't do that, then basically you are making a conclusion which maybe may cost the company something, because if you want to make it 5, they may have to spend some money, as opposed to if you have told them, no, it is 4 and 6 is equally good, they could have, done with a 4 processor system or 6 processor system or whatever it is, right? So they would have saved the money. Ignoring errors in the input. And obviously your workload is not perfect, and you have to have that sensitivity analysis as well, is that what are the variance in the input. Improper treatment of outliers. So you have 100 results and one of them is over there, everything else is here. So that's an outlier. What do you do with it? Do you ignore it? Do you include it? If you include it, everything moves over there. And if you ignore it, then everything is here, right? So very different system, very different conclusions. And that's where the system knowledge comes in. There is no mathematical answer to this thing. You go and read the books on performance analysis and they will tell you treatment of outliers. Here is a mathematical system. But these are mathematicians writing the book. They are not really, you cannot use that in the real world. Okay? In the real world, you have to go to the systems guys and ask them, why is this point over here? Is this a real system behavior? Did I make a mistake? If this system is there, if it is a real system, then you have to include it. If it is not, then you don't have to include it. So the thing is, there is no mathematical answer. This is where I disagree with the mathematicians, that you can just mathematically figure out whether it is an outlier or not. So there are methods and methods of figuring it out, but that is all mathematical. You are assuming that it is normal, and if it is more than 3 standard deviation away, and therefore it is an outlier. Right? And you might miss the important thing about the system. Assuming no change in the future, and then they forecast. So there are forecasts in 2050, United States will be below and that country will be over there. So they are assuming that nothing will happen between now and 2050. There are 30 years there. I don't know, maybe 40 years now. System will be as it is today. And that is not what the real world is about. So the system changes, so you have to somehow allow that the possibility that system will change, and actually it turns out, as you think about forecasting, and we'll talk about that the confidence interval grows very fast, in the sense that you can be confident about if you make a forecasting for tomorrow. But if you make a forecasting for a year from now, you could say, well, I am saying 5%, but it could be anywhere from 0 to 25%. And then 2 years from now, you say, well, I am saying 5%, but it could be anywhere from 0 to 50%. Your interval keeps going up, and so you cannot just pinpoint the answer. And so that is one thing, is ignoring variability. And I could go on the list actually, but I think these are all, maybe I should go through the list anyway. So let's see. Ignoring variability, we already talked about, so you have to make sure that you somehow give some idea of variability. Too complex an analysis. And then there are people who are real mathematicians, and they will come and they present the equations and equations and equations to the management. And what is the management going to do with it? Very impressed. This guy knows a lot. I don't understand a thing. All right? And then obviously they will not use a thing. If they don't use a thing, then your time is wasted. And so therefore, if you do any complex analysis, you have to keep it in your pocket and you have to present it in a very simple way. All right? So that is what another thing we will talk about. Improper presentation of results. So how to present it properly. Ignoring social aspects. So here's the thing, I mean, most people, when you do the analysis, your job is to change people's mind or to make sure that they buy your way of thinking. They buy that, okay, we should have 4 CPU system. Your conclusions, they buy your conclusion. You are writing a paper that X search is better than Y search. And so you want people to use X search in future from now on, right? So you are really selling that thing. And so there is a whole thing about the technology and technical aspect, which in the real world is the social aspect. And so the management and all that. So that's something, if there are some people who are really totally technical and they miss the whole world because they miss that part. Because so you cannot just be totally technical. Omitting assumptions and limitations. And the second thing is that whenever you present the results, write a paper, make sure that you say these are the things we assumed. All right? Because if any of those assumptions is not right, then this thing will change. And most people just ignore it. In fact, all the queuing theory people assume exponential of something and then they just forget it that this was assumed. All right, this is only a partial list. The bigger list is in the book and you can read that. What I want to do next is, any question about the common mistakes? Okay. So what I want to do is checklist for avoiding common mistakes. Is the system correctly defined and goal clearly stated? So you have to check off yes for all of these questions. First, you understand what the system is. Okay. And the system boundaries. So for example, if you are working for a disk company, your system is the disk. If you are working for Dell, your system probably is a computer that uses the disk and CPU as well. If you are working for bank, then your system is that whole big data center that you are setting it up. And so the system definition changes and you have to know where exactly your system is. If you are working for a company that designs the head for the disk, that is their system, that little head. And so, for that you have to put the right goals and the right thing. Okay, the goals are set in an unbiased manner. Have all the steps of the analysis followed systematically. So we will go through these steps in the next few slides. Is the problem clearly understood before analyzing it? That's the thing. Is that if you don't understand the problem, then you are going to get the wrong answer. I mean, the chances of your getting the right answer are smaller than if you understood the problem, right? So don't start just the simulation or analysis before you understand the problem. Are the performance metric relevant for this problem? So correct performance metric, correct workload, correct evaluation technique, those are the next 3 things. The list of parameters that affect the performance complete. So first of all, you make a big list of everything that could possibly affect the performance. That is the parameters. And then you select some of them as a factors. That is the last thing. Have all the parameters that affect the performance being chosen as factors to be varied. Actually, not all the parameters that affect the performance significantly have been chosen. This thing is, something could affect 0.001%, but who cares? Right? So that affect the performance significantly have been chosen. I should make a note of that. All right. So this is the slide 1. Can you give me the slide number 2?
Which one?
Handout 2. Okay. All right. And the list goes on. Actually, the experimental design, level of detail, and I think this is in some sense the application of the mistakes. And we have said most of the stuff that we need to say, but this is just presented as a checklist. So I'm going to skip to the next thing, how to do it right. So the systematic way is to write the goals and then list the services. And I will talk about what is a service. And that is the key. So you list the services and the outcomes. That will help you select the matrix. All right. Now, there is an example where we talk about services. Right now, I think if I start defining the services, then it will be a little bit off track. So I'm going to wait on that one. So list the parameters. Then you list everything that could affect the performance, and then select some of those parameters that you feel are the most significant one. Then you select the evaluation technique. And for each of these, actually, I have almost a whole chapter for each of these, so we'll worry about that. I have to select the evaluation technique, how to select the workload, how to do the design of the experiment, and then analyze the data, present the results, and go back to the step one again. This is the whole world is cyclic in the sense that once you have done the analysis, if it is good, you will have to redo it because they just want you to do more of the same thing. If it is no good, you will have to redo it or find another job, basically one of the two. Is that, and they will say, well, this is no good, just do it this way, another way. All right, so let's start with the steps one by one. System definition. So basically, system definition is very variable, so I cannot just say that this is always a system, but here's an example that you are working on some network analysis, and therefore there is a client, there is a network, and there is a server, right? And you want to study the performance of the network, really. Okay, so that's your system. That network is your system. Now, the network does offer some services. What can you do with a network? You can transfer a file, right? So that's, we could, and you could do a lot of things. You could say, well, I could send an email, I could do remote teletype, and there are many different kinds of services you can get on the network. But for the time being, let's assume that we are just interested in file transfer. Okay, so that is one service. If you have that service, for that service, then you have to write the metrics. What is it? What is a good file transfer? Why the file transfer would be considered better than the other? First of all, that the number of errors, number of packets that are lost is important. A number of times the network goes down is important. And then the rate, time, and resource per service. So how many packets per second can you send? How long does it take to send one packet? And how much CPU you used up for that one sending one packet? Now, we are going to actually go in more detail on this whole chapter. This is a whole chapter on metrics, but right now I'm just giving an example. So given to this example, you have to write that. And the resource could be the client, the server, or the network. How much of the client time is used for sending a packet? How much of server time is used for sending a packet? And how much of the network router time is used for sending a packet? So this leads to these metrics. Elapsed time per call. How long does it take to send a file? Okay, let's say you want to send a 1 megabyte file. It takes 1 minute. Maximum rate, call rate per unit of time, or equivalently the time required to complete a block of n successive calls. Actually, I should probably be using okay, well, I should probably be using transfer. So the maximum transfer rate per unit of time, or how many transfers can we do, and then local CPU time per transfer, local remote CPU time per transfer, and the number of bytes sent in each transfer, or each, call means each job or whatever it is here. So that would be metric. Now here I think these are all examples right now, and you can argue as to how did I come with these answers. And that is a valid question, but we will discuss that in the next chapter. All right, in the next chapter, we talk about metrics. In the chapter after that, we talk about the workload. The chapter after that, we talk about other things. So right now, it is just an example that somehow I came up with these metrics. Yeah.
Do you come up with the exact values for the metric before you actually go through the analysis?
Exact number, you mean how much data you want?
Yeah, how long do you want an operation to take?
Yeah, so there are two kinds of problems. One kind of problem is the design time. At the design time, they might have a design goal. And they will say, well, we really want people to be able to do it in sub-second, which is less than a second. Right? So then you put a goal. Right? Then there is a characterization time that you're buying a system. Right? I mean, there's not a design time, but then you're buying a system from Dell and you're buying a system from some other company, HP, and then you want to compare. At that time, you really don't have a number, but you want to make sure that you have 1 second here and 2 seconds there. So But you might still have a goal that your company says, well, we want to buy something which is less than 2 seconds. But so it depends upon the stage of the product. System parameters. Again, these are just examples, and I'm not going to, basically we'll go in a minute about how to do that, but system parameters, and again, for system parameters, there is no method. For metrics, at least I have a chapter. For system parameters, it varies with the system. But here is some example for this system. For this system, the speed of the local CPU could affect the performance. The speed of the remote CPU could affect the performance. The speed of the network could affect the performance. The operating system that is being used. So that was the first thing was the hardware, then there is the software, right? Operating system that is used for network part. And then the reliability of the network affects the number of packets that has to be retransmitted, so that affects the time. So these are the system parameters. Workload parameters. So when you load this system, which is a network, you have to have time between successive calls, the number and the sizes of the call parameters, the number and sizes of the, so basically, how often do you send the file? If you send the file very fast back to back, there may be one number, and as opposed to if you send them every 2 minutes, because the congestion in the network will change the number. Number and sizes of the call parameters, how long files you send. You send the files, small files, large files. Number and size of the results. So again, how much time does it take, and it depends upon that now. Now that's actually a question mark here. I think I'm going to remove that third line from the list. I'm going to explain you why. I think the number and size of the results would be more like an output rather than input. Workload is the input. So that I will have to double check as to why that got into the list. But anyway, type of channel is what kind of network it is. Other loads on the local and the remote CPUs, and other loads on the network. What else is going on the network? So those are all input. Factors. Now out of those, we could just select 4 things. The type of the channel, whether it is a remote pipe or procedure call. Okay. All right. I should have mentioned this thing in the beginning, that this is a case study which was done by somebody at MIT actually. And that time they were doing research on RPC or remote pipes. So they had 2 different methods of doing. This was not a file transfer thing. This was, so I misunderstood that one. This is about the remote procedure call. So you want to execute something on a different machine, right? And there are 2 methods. The method that they were working on called remote pipes, and RPC, which was the usual thing in those days. So they were comparing those. So there's basically, that is the first factor they want to study.
Can you explain that again?
Remote procedure call? Okay, so procedure call, you can just call a subroutine, that is called a procedure call, right? I mean, that makes sense. But if it is done on a remote machine, then it is called remote procedure call. So now network is involved. And so that's why we were using the word call all the way through when I was thinking of the file transfer. So this is not a file transfer, this is a subroutine call on the other machine. Right? So size of the network, whether it is a small network or a large network, long distance, because the distance will affect the, right? So the students, this is actually students' result, they selected. So now that makes sense actually. The previous one, the number and sizes of the results make sense. You know why? Because the results have to be sent back. When you make a subroutine call, you send the parameters and then you get the results back. So if the result comes out this big, the total performance would be different, right? So that thing is valid. The sizes of the call parameters. So whether your input is small or large, and the number of consecutive blocks. And so they selected block sizes of 1, 2, 4 binary numbers. So anyway, so this is the actual study that somebody did, and they selected those as the factors, and they selected the following things as not a factor. So type of the CPU and operating system. So they probably assumed Multics or whatever they were working on. They said we will not change the operating system. They could have done that for Multics and Unix and whatnot, but they just selected one type of CPU among the operating system. They ignored the retransmissions due to network errors, and they measured under no other load when there were no other load on the network. So this is their assumption in some sense, and when they wrote the paper, they put that in that this is what we assume. So obviously the results will not apply to other operating systems. They will not apply to other type of CPUs, and so they are making it clear. Okay. Evaluation technique. They selected a prototype is implemented, so therefore they selected measurement. And they were going to use analytical modeling to validate the measurement. And we'll talk about that also when we talk about the techniques selection. For workload, they were going to use synthetic programs generating the specified types of channels, and so basically they're just going to remote terminal kind of thing, as we said, use another computer to get the workload in. And then they also used null channel request to figure out how much resource is used in monitoring and logging, because they were monitoring and logging at the same time. CPU was being used while it was used for the other work. So then they also did zero workload to measure how much CPU is being used for those things. Experimental design, they used a full factorial design, 2 raised to 13 by 11, 2 raised to 3 by 11. So where does the 11 come from? You see there are 3 factors, each of them are 2 values. So remote procedure call, that first type of channel, there are 2 types of channels, 2 sizes of the networks, and 2 call parameters, but 11 is the number of consecutive calls, right? You have 2 raised to 0, 2 raised to 10, right? So total you have 11 numbers there. So they selected 2 raised to 3 times 11 full factorial design. And again, that may not make sense right now, but what does that 2 raised to 3 times 11 means? But we will talk when we come to the experimental design. For data analysis, they used analysis of variance for the first 3 factors and regression for the last factor. Now, this is the question you had, how you do that. And so what you do is, you really have 11. Now, this is something advanced right now. Okay, so let me not answer this right now. So basically, they selected that for the block size, they will do a straight line fit kind of thing, regression. But for everything else, they will use this analysis of variance. And data presentation, the final result will be plotted as a function of the block size, and then they're going to plot the results so that you can see the 8 lines. Anyway, so this particular chapter actually is more of an example right now. I mean, in some sense that we tell you that this is one example of a good analysis. However, how did they get to any of those steps? That is the next chapter, is that how do you do it right. But summary of this chapter is that the analysis technique, the metrics, and the workload, they all depend upon the goals. So first you have to set the goals. And the metrics depend upon the services. So actually we go into more detail as to how you list the services and how you list the metrics. And the system and the workload parameters determine the right size of the experiment, right set of the experiment. So you have to list the parameters and the factors, and then you can design the experimental design like they did 2 raised to 3 times 11 design. Correct analysis and presentation of the results is important, and so they basically, you can't see read the paper right now, but basically that is something that we teach you how to do that too. So here is an exercise, 2.1. From the published literature, select an article or a report that present results of performance evaluation study. Make a list of good and bad points of the study. What would you do different if you were asked to repeat the study? So that's the exercise, and probably that is also the homework. Homework is exercise 2.2. So let's read the 2.2. 2.2 is choose a system for the work performance study. Briefly describe the system and the list. So here is what you have to do. This is a kind of open problem. Whatever you feel comfortable with. All right? You're comfortable with a computer, with a network, with a database, with an algorithm, with a search technique. Just think of your system. Make a list of services that it provides. Make a list of performance metrics. Make a list of system parameters, workload parameters, factors, and their ranges. Select some of the parameters as factors and what evaluation technique you will use and what workload will you use, and justify your choice. So right now you may not get the right answer because I haven't told you how to get the right answer. All right? But this is before you know how to do it perfectly. Right now, just from whatever you already know, make a list of all this. All right? And don't worry about, because everybody will have a different system and different answer. So this is one homework where it is very difficult for us to just say, well, this is perfect. And actually that is true of anything which is art, is that we cannot say that this is correct or incorrect, that much. But if you're way off, then we will tell you, no, I think you're way off. You just missed this whole big thing. Yeah.
When you say evaluation technique, isn't that all everything else in the list? Doesn't it matter how
Okay, so for evaluation technique, all I want you to tell me is one of the three things, whether you are going to do measurement, simulation, or analysis. Okay, so analysis means modeling, sorry. Measurement, simulation, or modeling. Factors, everybody understands what is a parameter, what is a factor. Right? Okay, so you understand that. And then matrix, you understand. Matrix could be, one of those things, how time, resource. Let me see. We use the word here. Matrix is the rate, time, and resource. How many per second you can do? How long does it take for each thing to do? And how much of the resource is used. So you write down the matrix, and as I said, this one is more to just see. I mean, if your answer is different after you have learned the other things, the correct things. All right. So don't worry about being perfect. Now, so read chapter 2. Submit answer to exercise 2.2, assuming system is a personal computer. Okay, so we limit it actually to personal computer. The solution should be limited to 3 pages and submitted by email to jain@worcester.edu with subject of homework 2. This one. Exactly. Don't change anything because my computer is automatically going to catalog these things. If you make a space somewhere there is no space, it will get confused. All right. So send me by email. Is that homework clear?
Due Monday or Wednesday?
Okay, Wednesday. It could be due on Monday, but you could do it on Wednesday. Yeah.
I'm not sure understand what is meant. The system is personal computer.
Okay, all right. What is the system is a personal computer? Yeah, that's a good question. So, I am in the market for a personal computer. I want to buy a personal computer. All right, you want to buy a personal computer. And let's just assume that you want to buy a laptop. All right. So that's our problem. What will you select? What will you do? What is the methodology and things like that?
In terms of the specifications of the computer that I would choose?
Well, I mean, so the thing is, let's make it like this, that we are a company and our company wants to buy, let's say, some computer, maybe 100 computers. You are in charge of performance analysis. So what will you do, I mean, in terms of, selecting and comparing different computers maybe. So you are asking whether you are, say we are in the buying business, but we have 2 or 3 people who are trying to sell us, right? So we have to compare them, right? So how will you compare them?
Shouldn't we know what the workload is?
Huh?
We need to know what the workload is.
Yeah, so just think of some workload. I mean, just think of some company uses for something else. Yeah, you have a question there in the back? Yeah, you a guy, huh?
I was wondering what kind of company. Is it like
I know. Okay, I hear the thing. I know. Okay, hold on. Just assume, okay, that you are working for company X and this does Y, and therefore I'm selecting this as the workload. Okay, because if I gave you everything, by the time we'll be done with the problem. So just assume right now. Okay, this is very imperfectly specified problem. Purposely is because the answer will be different. I want you to think and justify. Yeah.
I had a quick question, Renz, about the network and the transmission.
Yeah, it's too early to answer that one. See, thing is, yeah, that's a good question. But basically, what you simulate or what you measure, what you analyze, it will come slowly. Okay. Yeah. All right. So this is our first homework. Actually, it says homework 2. All the homeworks are numbered by the chapter. So homework 39 doesn't mean it will be 39th homework. It could be even 25th homework. So so they are numbered by the chapter. But okay, and here is the common mistake in homework 2. Not defining the system. List of metrics not based upon the services. So people will list the services but not worry about them when listing the metrics. Mixing system and the workload parameters. So like we had this result thing, make sure that the workload is the input and not inside the system. Factors not in the list of parameters. So when you make a list of factors, make sure they are part of the parameters. Right? Now there is one more homework. This is called homework 1. Project homework 1. So this one actually is totally different. We haven't thought about this, but basically this is getting ready for the project. And any project, regardless of what you do, you'll have to do this searching. So this is about the web search. All right. So search web pages, books, and journal articles from ACM Digital Library. Some of you don't know what is ACM Digital Library, so that's why I wanted to teach you. Figure out what is ACM Digital Library, but that means you go to the library, not in person, but online, library.worcester.edu, and figure out what is ACM Digital Library. They have the whole ACM Digital Library there. Search, applied science, Compendex, AVI Inform, complete, and novel databases at Olin Library for one of the following topics. Computer systems analysis, computer system modeling, simulation. So basically the last words are different. Analysis, modeling, simulation, experimental design, queuing theory, right? Just one. You don't have to do all 4, 5. On the web, try the following search points. Library, Scholar, books. Now, everybody has used books.google.com? Okay, well, this is the time to use that. That's why I'm giving you this homework. If you have never used books.google.com, figure out what that is. A9.com, what that is. Figure that out, search. Sightseer, Cyrus, WorldCat, and searching guide. So you see all this. This will get you used to how to search for the latest. This will be useful not just for this course, but for any graduate thing that you're doing in general. So this is research techniques. Now, ignore all entries dated 2007 or before. So I don't want anything more than 5 years old. All right. List the others in the following format, only 5 each. Actually, it says up to, just don't make up to, just make 5 each. If you have 4, you get 1 less point, so 5 of each. If you have to get 5 books, and those have to be listed as the author, title, publisher, year, and ISBN. You have to get 5 web pages. You have to write a title, URL, and 1-line description. Okay, and this is important. You have to write title of the page and the URL of the page, and then 1-line description of your own. What do you think this that page does? For the magazine articles, you have to write author, title, and complete bibliographic data. So generally for the magazine, you have to write, volume number, the issue number, the year, pages, and all that. So the way you write references for the articles. For journal articles, for 5 journal, magazine, periodicals. Okay, so you are also trying to find out not only books, you also have to find out journals. So there are journals on your topic. So whatever topic, well, actually let's say you selected experimental design. There are journals on experimental design. So we are talking about the whole journal, not a paper in that journal. So for that, you write down the title, publisher, and the URL for the journal. Is that clear, the last part? Right? Okay. For books, first item above and journal fourth item above, find the items that are not devoted primer, that are and not have any item that have the topic as subset. So this is a mistake people make. This time they are very clear as to what we are searching, but in every other course we ask them to search for different topics. So here I think when you search for the word performance, wherever you're going to search for the books, almost every book has the word performance inside it. Performance is a very common word, right? So your hit list would be very noisy. You are not looking for any book that has the word performance in it. You are looking for performance books, right? So please don't list the books that have nothing to do with the performance or whatever you're doing, experimental design or modeling or whatever it is, right? So that is another thing you have to do, is that while searching for these things, you have to really know the density of these things, and sometimes that will come out by looking at the title. You don't have to go and read the book, but from the title itself, it is clear that this book is not about performance. This book is about medical something. All right. Serially number the references and submit electronically to Jain at worcester.edu with this homework, this subject field. Make sure that you don't make any mistake in the subject field. Make a list of other interesting search points and share with the class. Now, this is not the complete list of the search points. Although, like the search points list are kind of nowadays decreasing faster and faster because many of these things are, but anyway, you might find something different which I didn't put in the list. So we can discuss that. Now, when you search it, this is the list of mistakes that people made in the last time or before last time, and I don't want to make the same mistakes. I'm giving the mistakes right now. Listing older books. I don't want anything less than 2000, earlier than 2007. Listing books or magazines that have little to do with the topic. So simply because it is a Google hit doesn't mean that that's a hit. You have to put your brain along with the Google. It may show up in the search engines because of minor mention of the topic as well. Web pages, no one-line description. People forget to write that one line. I need that one line of what you think that page. Because if you found this, you will go to the page at least. But you cannot write a page simply because it hits on Google. You have to go to the page and see whether this is about that, and then write one line. Incomplete bibliography of journal articles. You need the volume, issue, year pages. Missing journals. Need names of journals dealing with the topic. So people forgot that this is journal I'm looking for, not a paper in the journal. Right? Any question about this? I've tried to make it as specific and clear as possible. Yeah.
So you first choose one of the 5 subjects?
Yeah, you just choose one of the 5 subjects.
Then you search those?
For that particular thing, yeah.
Okay, just for that particular, that you chose.
Yeah.
So you want references, 5 book references, 5 web page references, 5 magazine, and 5 journals.
Okay, so that is total of 20 items.
Okay.
And so, okay, well, that's the end of